Hi, Mick McQuaid here. Welcome to the next to last video for day 5. I guess this is the third video and third of 4 videos for day 5. And in this video, I'll talk about qualitative predictors. These are just some sort of miscellaneous topics about multiple linear regression, qualitative predictors, extensions of the linear model, mainly extensions to include an interaction term or to include a polynomial term, and about 6 potential problems with the linear model that we're just going to cover at a very high level. And then that will be that. So let's get started. Okay, so qualitative predictors are the first thing to talk about. Now, we've already talked about qualitative responses, and the way that we're going to deal with qualitative predictors is much the same. So here's an example of a data set with, this is the credit card data set, and it has 4 qualitative variables in it: gender, student status, are you a student or not, marital status, are you married or not, and ethnicity, which oddly is broken into 3 groups: Caucasian, African American, or Asian. I guess this is just for the sake of simplicity or something. So with this, so let's take gender first. Let's take a quick look at gender. So the way that we're going to deal with this qualitative variable is to encode it as a 1 in one case and a 0 in the other case. So this is an example of a binary variable, or a variable with 2 levels. And the 2 levels are male and female. And so we're just going to arbitrarily choose 1 to mean female and 0 to mean male. It doesn't matter which one we choose for which thing. What's going to end up happening is we're going to wind up with a model that looks like this. And if this value is 1, then we will have this beta 1 term. If this is 0, then we won't have this beta 1 term will drop out. And so this will be the model if the person is male. And this will be the model if the person is female. So in other words, beta naught is going to tell us about males, and beta 1 is going to tell us about females. So let's take a look at how that plays out. So in this particular case, what we had was a coefficient. So this is a balance and gender. So the output is balance. So for each unit of gender, so the intercept is male. So the male carries an average of balance of $509. If you're a female, you carry an average balance of $509 plus. You see, adding each unit here adds this much to the Y value. So being female adds $19 to the credit card balance. So this fulfills a stereotype about females. Oh, wait a minute. Is the stereotype really fulfilled here? An extremely large standard error is present, and that leads us to an extremely small t-statistic, and that leads us to a ridiculous p-value. So there's a 66% chance that if this number were 0, you would see this t-statistic or a t-statistic larger than this. So, sorry stereotypers, looks like this number might as well be 0. There's really no, we have no evidence. We don't have any evidence to reject the idea that based on gender, anybody has a balance other than $509.80. Now we could do this in different ways. So I think that they show, or they talk about doing it this way. If we encoded males as 1 and females as 0, we would have gotten a beta naught of 529 and a beta 1 of minus 19. And another way that we could do it, which I don't see at all, this isn't as common, I think, is because it requires 2 calculations instead of 1, is to encode them as 1 and minus 1. So if we encode them as 1 and minus 1, we would get, the result would be, let's see, we would get 519 as a result, and then we would get, that's what we would get for beta naught. And then for beta 1, we would get half of the difference. So if we add this difference to if we add this difference to beta naught, we get the amount for females, and if we subtract this amount, we get the amount for males. So that's just a different way of coding it in, I think, a more cumbersome way. So I don't really see people doing that. Now, suppose that we have more than a binary choice. So in the case of gender, we only had a binary choice, but in the case of ethnicity, we had three choices: Asian, Caucasian, and African American. So we always will need one fewer variable than we have choices in order to encode this properly. So what's going to happen here is we have essentially on-off switches. This X1 here is an on-off switch for Asian. This X2 here is an on-off switch for Caucasian. And the base case, if these are both turned off, is going to be African American. So what we're going to get is the balance in beta naught, the balance for African Americans, and then we're going to get the difference in beta 1 for Asians and the difference for Caucasians. So let's see how that regression played out. And here again we see is this a stereotype? I don't know, actually, if this is certainly it's simplistic enough to be a stereotype, but let's say that the African American on average carries a $531 balance, and the Asian carries an $18 less balance than that, and the Caucasian carries a $12 less balance than that. So if this is a stereotype, then I guess it would be a stereotype that the Asian is thrifty or something like that in comparison with the other two. So this is all really great if we wanted to play into some stereotype, but then, oops, we take a look at the standard error, and here again we find that, darn, there's no evidence for it at all. In fact, based on ethnicity alone, we really basically get that the average balance is $531, and these two numbers might as well be zero. There's an 82% chance that if this number is zero, we will see a number of equal or greater magnitude to this number. And if this number is, there's a 77% chance that if this number were actually zero, we would see a t-statistic with this magnitude or greater. So anyway, and we can just continue to do this for more and more of these, and we just always need more we need one fewer indicator variable than we have categories. So if we have a category of 4 that can take on 4 values, we need 3 indicator variables. And the reason that we need that, by the way, the reason that we need them is because we need these betas. We need each of these betas to be unique. So you might be tempted to think that, well, two binary numbers can take on a total of 4 states, but that's not good enough because that isn't going to give us these coefficients. We need, you have to think of these as separate on-off switches for these coefficients, and beta naught being a separate baseline. In fact, we would always call this the baseline. Okay, enough of that. So let's talk a little bit about extensions of the linear model. And one of the extensions we already talked about a little bit. We talked about the, let's see if I can find it here. Yeah, we talked about the TV and radio. And we saw that in the case of the graphical model of the TV and radio advertising, that we had a saddle shape, and that when the amount of TV and radio advertising was equally mixed, the model performed better than for the lopsided cases of lots of TV spending or lots of radio spending, where we were able to better predict the amount of sales in the middle. So we definitely want to include a term that takes care of that. And the way that we do that is we multiply the amount of TV sales times radio sales, and we include that. We just multiply these two things together and we include that, and we call that an interaction term. And in this case, it works quite well. We get a very clear contribution here to the model. Now, this isn't telling us, by the way, that radio and TV advertising, this isn't telling us anything about radio and TV advertising per se. This is telling us that we can better predict the result of sales from including radio and TV advertising as a product. And in fact, it's quite a bit better. I think somewhere here we see the R R squared, yeah, the R squared for this is 96.8% compared to only 89.7% for the additive model. So that's quite a lot. So 69% of the variability that was left over after fitting the additive model has now been explained by the interaction term. So we definitely want the interaction term there. And we often want interaction terms. And sometimes we can figure out that we need interaction terms because of intuition, and sometimes from looking at a graphical model. Now, here's an important principle. If we include an interaction in a model, we should also include the main effects, so that would be TV and radio separately, even if the p-values associated with their coefficients are not significant. So back here we saw that the p-values were significant for all of them, but even if these two hadn't been significant, if this one is significant, we want to include its components. That's a basic principle. And the rationale is actually given here somewhere. I don't know, where is it? Here it is. If x1 times x2 is related to the response, then whether or not the coefficients of x1 or x2 are 0 is of little interest. Well, that's not much of a rationale. Also, if x1 and x2 is to some extent got to be correlated with x1 and x2 individually. x1 times x2 has got to be correlated. So leaving them out will tend to alter the meaning of the interaction. So that, I don't think that's a really great rationale, but that's the way it is. Okay, and then here's another example. This is with the credit card data. If we include income, okay, so this is an example where we can see some nice graphical evidence. So here's in the case of the credit card data, we have this situation that the slope is different. So this is an additive model, and this is a model with an interaction term. If we include the interaction term, we find out that the non-student has a different slope from the student. And that's a good indication that there is some interaction going on, although we would still want to check the p-value, the t-statistic, the standard error, whatever. Okay, the other thing that we might want to include is a quadratic term. So if we think back to the auto data we looked at before and miles per gallon versus horsepower, we mentioned that this seemed to be a somewhat curved relationship. And indeed, it not only does it look curved, but here's a curve that fits it pretty well. Let me just zoom in a little bit on this. So this orange line is the least squares line for horsepower versus miles per gallon. Using horsepower, I should say, to predict miles per gallon. And this blue curve here is using horsepower plus horsepower squared to predict miles per gallon. Now that's clearly a better model. I mean, just glancing at it, you can tell it's going to be better. We'll look at the statistics in a second, but it looks just at first glance like it's a better prediction. Now, one question that the book raises is, if horsepower squared is so great, why don't we add horsepower cubed? Hey, why not add horsepower to the fourth? Hey, let's add horsepower to the fifth. And so they've done exactly that. They've added horsepower squared plus horsepower cubed plus horsepower to the fourth plus horsepower to the fifth and formed this green line, which is clearly an exaggeration. This is not a great fit. We were fine with just the quadratic term. And it sort of reflects there's a little bit of an art to doing this. You want to do as little as you want to add as few terms as possible to make it possible to interpret the model, but clearly adding horsepower squared is helpful in this model. And let's take a look at the statistics. They're here somewhere. Yeah, so what we see here when we look at the statistics is that the standard error for the horsepower squared term is very small, and so consequently we have a p-value that suggests that we would be. It is very unlikely that this is 0. If this were 0, there's a 0.0001% chance of seeing a t-statistic this large. Okay, so and now we have this is called polynomial regression. We'll talk about polynomial regression later, but it's very typical to modify a linear model with just a quadratic term. That often helps us out a lot. Okay, now there are 6 basic problems with linear regression. And any linear regression course, see, if this were a course entirely in linear regression, we would spend a lot of the course dealing with these 6 problems, because it's kind of a dark art to figure out how to overcome these problems. And people get paid just to do, particularly in the insurance industry and the credit industry, people get paid just to figure this stuff out. And so it's important stuff, but it's not the center point of this course. This course is just going to introduce a number of methods, of which linear regression is just one. So we're just going to give a very high-level coverage of these 6 issues. Okay, and so the first one is non-linearity. And by the way, for almost all of these, there's one tool that is really helpful, a graphical tool that's really helpful, and that's what we're going to look at initially here with the nonlinearity issue. But we're also going to see this tool used again and again, and this tool is called a residual plot. That's what we have right here. We have 2 residual plots. So if we look at the auto data set, the miles per gallon and horsepower data set, on the left we see the additive model without horsepower squared. On the right-hand side, we see it with horsepower squared. And what this plot shows us is the error terms associated with their fitted values. So this is the error terms and the predicted values. And what we want to see here is no pattern at all. What we want, the error term should just be random noise. So here we see a strong pattern. We would like this to just be the same throughout, just blah, 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 blah throughout, like this. Basically, here we see no pattern, or very little of a pattern. So here what we guess is that we've left something out of the model. If we have a pattern left over in the residuals, if the error terms show some kind of a pattern, then our model is not good enough. We need to find something else that we're missing that is contributing to this pattern. And in that case, in this particular case, it was horsepower squared. Once we took horsepower squared into the model, we were left with a lot of random noise. So the residual plot is a useful tool for all of this, for almost all of this stuff. Correlation of error terms. So here we're going to see some more residual plots. So if the error terms are correlated with each other, they will look very much like this. This is a high degree of correlation. This is row of 0.9, row of 0.0. I should say row is, we haven't been introduced to that letter row, but it is the sample correlation coefficient that we learned about earlier. And that sample correlation coefficient is also called R. This is simulated data, so the row signifies that this is the real correlation, not just the sample correlation. We usually use Greek letters for population parameters and Latin letters for sample data. So the lowercase r, which is the square root of r squared for the case of 2 variables, is what this is. And if these are uncorrelated, it's just going to look like this, static. If they're highly correlated, it's going to look like this, a series of hills and valleys. And if there's some correlation, we're going to see some of this pattern. So unfortunately, what you're always going to get is something in between these. So this is again a dark art, trying to read this to see if there's correlation in it, to see whether you see, you might count up the number of directional changes here, but that wouldn't make a good metric. You really have to look at the residual plots. Okay, so non-constant variance of error terms. What does that mean? Well, this is shaped like a horn, and this looks random. There's no information. Any place where I go along this line any of these values are equally likely. So that suggests that there's no change in the variability. Here, if I go along this line, there's much more variability over here than there is here. This is kind of horn-shaped. And so this is called the statistical term for this is heteroskedasticity, and the statistical term for this is homoskedasticity, meaning that the variability is the same. Heteroskedasticity meaning that the variability is different, and you often get this kind of shape here to the residuals. So it's very important to do residual plots. If you do this, then there's a pattern that you've missed, and this is just a cooked data to show this. The other situation that you might get is a barbell shape to this, but the horn shape is the really common thing that I see a lot. Okay, then we have outliers. So outliers are potentially problems, but potentially not problems. So here's a case of an outlier. Point 20 here looks like a bit of an outlier, but if we plot the residuals, it looks like very much of an outlier. And if we somehow standardize the residuals according to their the assumption of normality, it looks like even more. There's even greater distance between here and the top points than there is between here and the top points. So these outliers are suggest that there might be a problem. It may be that we need to remove them, although I personally urge conservatism in removing outliers. Outliers sometimes are solid, valuable evidence. They're not necessarily just errors. There are certain outliers, though, that you probably need to remove. High leverage points. So here's our same outlier again, this point 20, but here's another outlier, point number 41 here. This outlier is quite powerful. This outlier has the power to change the regression line. So the dashed line is the regression line without without point 41. The red line is the regression line with point 41. So look at the difference in the slope there. It's actually dragged the slope up. It's tilted that 1 point has tilted the whole line quite significantly. So I think the cautious thing to do would be to remove point 41 in this case. And we'll see if we do a residual plot here, it looks really outrageous compared to the others. It's so far away from anything else. The pure distance here is not as big of a deal because it's straight above these. It just indicates greater variability. This is going to increase our perception of variability, but this is going to increase our perception of the shape of the data. So I urge caution in removing outliers, but I urge you generally to remove high leverage points. Oh, and how do you know that it's a high leverage point? So looking at the graph is not enough. Looking at the graphic is not enough. We can, if you suspect high leverage points, if you have some outliers and you suspect high leverage points, you can actually calculate leverage, and this has an average value of the number p. And this is the p that's the number of dimensions plus 1 over n. So on average, that will be the leverage of any given point. And it can vary between 1 over n and 1. So if it's much larger than this, if it's between here and 1, then there's a good chance that you have leverage and that you should remove that point. Okay, and then the last of the 6 issues is collinearity. So here's an example of where there's no collinearity. Limit and age, this is in the credit card data, limit and age are not associated with each other at all. This just looks very random. Rating and limit are highly associated. Anytime that rating is 6,000, anytime that limit is 6,000, rating is 400. You can easily tell one from the other. You just go up from here and you can tell almost exactly one from the other. So these are highly collinear. And that is potentially a problem. And here's how you can see that that's potentially a problem. So remember that what we want to do is choose our beta values, beta naught and beta 1 and so on, to minimize RSS. So here's a plot of two unrelated variables and RSS. So this is a contour plot. So imagine you're looking down into a valley, or into a bowl, I guess you would say, into a lake or something. So here's the value of one of these variables here, and the value of the other variable here, and then we're looking down at RSS, and these contours are equal values of RSS. So all along this line is a value of 21.25. This is similar. Hopefully you've seen contour maps of elevation that look like this. And so we can easily see that the lowest point here is this point in the center. There's no question. It's pretty obvious what the minimum RSS is here. On the other hand, rating and limit we just saw above are highly collinear, and here's the same kind of map for them. And it is not at all obvious where the minimum RSS is, because this value here is almost the same as this value over here, almost the same as this value over here. This is highly unstable. There's very little room for error here. So this is a case where we suspect a high degree of collinearity that may be problematic. And luckily there is a statistic we can use somewhere. Here it is, variance inflation factor. Here's a statistic that we can use, and most statistics software is set up to actually calculate it for us. A statistic that we can use to figure out whether or not multicollinearity is a problem. And this is found in the following way. We do a regression of one of the predictors on all of the other predictors. So this is a regression that doesn't involve the response variable. It only involves the predictor variables. So we use one of the predictors as the output variable, and the other predictors as the input variables. And then we take the R squared that results from that, and we subtract it from 1, and we divide 1 by that number. And if that number will be greater than 1, that number will get larger as the potential multicollinearity problem grows. And if that number grows to greater than 10, then you have definitely got a multicollinearity problem. And somewhere here it says if the number is greater than even 5, you probably have a sort of danger zone would be 5 to 10 would be multicollinearity, and 10 is right out. Okay, so that's it. That's pretty much the end of the 6 issues. So what we've talked about here have been the qualitative predictors, and using either a single indicator variable or one indicator variable fewer than we have classifications for the predictors. Then we talked about extensions of the linear model, and in that case we talked about either adding an interaction term or adding a quadratic term. And then we talked about the 6 potential problems: that the data is nonlinear, that there's a correlation between the error terms, that there's heteroscedasticity present, non-constant variance, that there are issues with outliers, and that there are issues with outliers that have a tremendous influence, and then finally collinearity. So, and then the only thing we have left to talk about today is going to be, oh no, we have 2 more things to talk about. So the next video is mainly going to be about exercise 3. No, that's tomorrow. The other stuff is tomorrow. Yeah, just the only exercise. Sorry, I got a little confused there for a second. The only other one for today is going to be exercise 3.7.8. So thank you for your attention, and I hope to speak to you again soon.